Hello, hello. Yeah. Yeah.
Hello, could you confirm once that you can see me, you can hear me, as well as you can see this presentation? Is it audible?
Yes, sir.
Okay, okay. Okay. Thank you. Okay, very good afternoon, everyone. My name is Ambuj. I am a research scholar at Agriculture and Food Engineering Department from IIT Kharagpur, and I'll be taking your live interactive session on the course Computer Vision. This course is taught by Professor Jayant Mukhopadhyay from IIT Kharagpur. And what we'll be doing, we'll be solving some of the previous week's, some of the objective questions based on the previous week's content. Okay. In front of you all, I'll be showing some of the questions. Okay. What you just need to have, take a notebook, take a pen and paper. Okay. And just write down what is the question, what is the approach. And after the session is over, I'll make the entire PDF available to you. Okay. As soon as the session is over, then please go through all the solution, all the approaches which I have formulated, okay, so that you can in the examination you would be able to solve these particular questions, as well as you will never face any problem also. Okay, this is the thing. So the very first question is this one. Let P be this particular matrix. Okay, this is a 3 cross 4 matrix. Okay, and you have to compute the camera center C in homogeneous coordinates, and your options have been given. Okay, and please note this particular question is related to the concept of pinhole geometry. Okay, pinhole camera geometry. And whatever the questions I will be taking in this particular session, they all will be more or less regarding this particular concept, that is pinhole camera geometry. Okay, pinhole camera geometry. And this is the very basic of this particular concept. Okay, that you need to find out what is the exact center, okay, of the camera. Okay, so this particular thing is very basic regarding pinhole camera geometry. Whatever the questions I'll be taking in this particular session will be more or less related to this particular concept. And at the end, I'll show you some of the applications, as well as in present lecture, I'll also show you some of the applications which would be research based applications. Okay, that I have applied in my own research. Okay, so bear with me. Okay, now you try to see the correct option would be A. Okay, minus 1, minus 1, minus 1, 1. Now you try to see that how the particular camera center in homogeneous coordinates from a given matrix P I have calculated. Okay. So in case of your pinhole camera or your projective modeling, a 3D point is given by this particular denomination. Capital X is equal to capital X, Y, Z, comma 1, and overall transpose of it. Okay. Now you see mapping this particular 3D point to a 2D image point. Why we are doing it? Because as I am a 3D object, okay, but in computer vision, everything is read through a camera. Okay, so a 3D object will be assessed, or the image will be captured through a camera. So for the camera, the every single thing which it is seeing in 3 dimensions will be in 2D dimensions. And now it is the role, our role as a computer vision engineer or an expert, to calculate various features, as well as various applications which we will be doing from computer vision, particularly domain. So how we will be doing this particular thing is that we need to know different types of features of the computer of the camera generated image. Basic features are pixels, number of pixels, what is the number of pixels, what is the length, what is the width, and various other applications are there. Okay, contours you can see, brightness, hue, saturation, value, all these things. Why we are doing it? You have to first understand. We are doing it because we want to know the information which is hidden from an image. Okay, for example, I am speaking in front of you and you are seeing me through this particular camera. Okay. My laptop's camera, you are able to see my image. Okay. But if this is the end, then there is no application of computer vision. Okay. Application of computer vision is when you are able to find out various types of spatial features. Okay, if you are able to find out this particular camera center, okay, then you would be automatically able to tell that how much distance is there between me and my camera, and why this particular information is very useful for various domains. Like nowadays you are seeing autonomous navigation. Autonomous navigation particularly wouldn't have been possible if you would not have been able to calculate the distance between the two or multiple cameras and the various features, okay, various features which are coming on the surroundings of the car. After a 3D map you are able to generate from different sensors as well as different cameras, okay, then you are able to plan a path, okay, of autonomous vehicle. So all these different applications, maybe it is augmented reality, maybe it is virtual reality, these generate from these very small concepts, okay. So this is the particular application, and this is the reason why we are very interested to denominate a 3D point in our 2D image point, okay, in form of our 2D image point. And now you try to see, because this course is fully mathematical, so I will be telling you applications so that you can have some basic interest, okay, as well as you can feel connected. So in between also, if you are having any doubts, please keep on asking, okay, please engage yourself. Otherwise, it would be just monologue. I want to create a dialogue. Okay. So if you are having any doubt, or you want me to repeat anything, or you are interested in the application of that particular concept, so please do ask me. Okay. Because I am having some limitations of time. That is the reason I have to cover all the 10 questions along with the concepts. That is why I myself I am not deviating much from the topic. But if you are having any doubt, any point of time, feel free to ask me. You can unmute yourself. Very few students have joined, okay, and ask me. Okay. I'll try my level best to keep you engaged through some practical applications which I have observed. Okay. Yeah. So in case of your 3D image point, if you try to map it in a 2D image, it would be made by small x equal to UVW transpose. This we already have seen in our previous 2 weeks. Okay. The projection matrix, if you see, it follows a relation R as matrix 3 cross 4. Okay. And small x is nothing but P capital X. This particular concept already has been taught. Okay, much in great detail in all the three sections, in all the three sessions. Okay, so this is regarding the mapping of a 3D object in a 2D frame of reference. Now you try to decompose this particular matrix P, which has been already given to you. Okay, you can always partition P as M oblique P4, okay, or M as subspace P4, okay. So M follows the relation 3 by 3. It combines various intrinsic parameters like focal length, okay, principal point, what is the skew, and what is the rotation of the camera with respect to the world, okay. Whatever image you are seeing, that depends on all of these three parameters. And in order to project a 3D image onto a 2D plane, we have to consider all of these. Okay, that is the thing. Now P4 follows the relation R cube. It encodes the camera's translation in the more familiar form. P follows this particular K R relation. Okay, and T. So making M equal to KR, you can always do it, or P4 equal to KT, but in the general denomination, you can always remember this particular partition. Okay, this particular partition would be very useful for you even in future concepts. Later concept you can see. Okay, now you try to see what is camera center. Camera center in the single 3D world point that gets sent to the point at infinity in the image, that is, it has no finite image location. Algebraic terms PC equal to 0 means if you take the camera, okay, to that particular distance, if you take the image, okay, to the to the if you reduce the distance between the image and the camera to zero, then you won't be able to find form any image that is written here in algebraic terms. Okay, In 3D world point that gets sent to the point at infinity in the image, that is, it has no finite image location. So P is a 3 cross 4 full rank 3 matrix. Okay. Null space in one dimension, and that is the null vector in C. So if you try to see the partition PC, that is M partition P4 equal to 0. If you try to solve, then at the end you will get this particular C as M inverse P4. Okay, multiplied by 1. The derivation has been already mentioned here. If you will try to just see it, you will very easily able to follow. Okay. Now you try to see what are the geometric interpretations R and T that I already told you in first slide. They describe how the camera is rotated and shifted into the world origin. And center C is exactly the world coordinate point relation R transpose T. Okay, where you write pk equal to k r relation t. Okay, that is tip of the pinhole camera. In projective terms, you can always transform a three-dimensional point to a two-dimensional point. Okay, why this particular C and the formula which I already showed you in the previous slide is important? Because of the triangulation of 3D points. What is triangulation? Triangulation is nothing but calculation of the x, y, z in three dimensions from two different cameras or a single camera. Both the approaches are having different type of formula and different type of mathematical denominations, but the goal is same. That is to triangulate, means triangulate, formulate what is the position, what is the x, y, z of a particular point. That is the triangulation. For your epipolar geometry, the line of sight from one camera center through a pixel defines the epipolar geometry. And the reconstruction of the scene, okay, and camera motion in structure from motion pipelines. Nowadays, various applications are coming. For example, 3D in your IMAX studios, 3D movies are getting projected. You are given 3D classes. With the help of that, you will feel that a line is just walking from the screen towards me. So how this particular illusion is getting created, that is very, very important, using this particular concept of epipolar geometry or the reconstruction of the image in three dimensions. Okay, means from 3D you are able to extract various 2D features, and from a 2D image which you already have captured, you are again able to reverse it into a 3D screen. This is the basic of AR and VR. Okay, augmented reality and virtual reality. That is the thing. Not deviating much from that topic. P matrix already given to you. Partition it in M and P4. Okay. M is, if P already has been given to you in the question. Okay. This particular thing. Now you just have to partition it. Okay. So first partition M will be 200030004. Okay. So this is the first partition M. Then P4 is the second partition. It will be 234. Okay. Now you try to see what is the now you try to see what is the camera center C. C is nothing but negative of M inverse P4. Okay. That is already I have showed you. Okay. So if you try to calculate M as a matrix, we already have extracted. Since M is a diagonal matrix, it is only having the elements in the diagonal columns. And you already know from your class 12 that if a matrix A is there, then A into A inverse is equal to identity matrix. So what you can see here, that since this particular matrix is only diagonal, what I will do, I will just inverse all the elements which are remaining. In not inverse means I'll make them fraction. If a element M P Q R is there, okay. If a element P Q R is there, just a second. Yeah. If the matrix is a diagonal matrix and all the elements are like this, PQR 0, 0, 0, 0, 0, and 0. Then from your this particular formula, you would be able to calculate that inverse of this will be 1 upon p, 1 upon q, 1 upon r, and all the elements, rest of the elements will be 0. Okay. So in the similar fashion, I have calculated this particular M inverse matrix. M inverse will be nothing but 1 by 2, 1 by 3, 1 by 4 in the diagonal. Okay. How this is coming, you can just prove. You try to multiply this particular M with this M inverse and you will be getting identity matrix. Okay. So from there, I have just formulated and I wrote down what is M inverse. M inverse will be nothing but 1 by 2, 1 by 3, 1 by 4. Otherwise, you can use that particular formula which I have told you in the previous session. Okay. 1 upon determinant of A into adjoint of A. And adjoint of A is already I told you, okay, how it is calculated, cofactor table transpose. And cofactor is nothing but minus 1 raised to power I plus j mij. Okay. So all three steps also you can follow. But if in future you ever see a diagonal matrix, you try to just calculate the inverse matrix in shortcut like this. Okay, that is the thing. Now you try to compute M inverse P4. Okay, M inverse P4. P4 already I have just separated from here. Okay, this particular thing, and now you try to multiply. Okay, so if when you will multiply, you will be getting this particular thing. Okay, matrix multiplication already you must be knowing. We would be doing row by column. Okay, since this particular matrix is 3 cross 3 and this particular matrix is 3 cross 1, so m should these two should always be equal. Okay, for matrix multiplication to happen, 3 is 3. Okay, if a matrix is I cross j, another matrix is p cross q, then j should be always equal to p. Okay, for matrix multiplication to happen. Okay, and the resultant matrix would be of the dimensions I cross q. Okay, means 3 cross 1, 3 rows 1 column. So similarly you try to multiply every other element. Okay, row cross row by column. Okay, try to multiply and you will get it as 1 1 1. Okay, all three rows will be same. Okay, that is the thing. Now you try to calculate C is nothing but minus this particular matrix minus M inverse P4. Okay, so M inverse P4 already I have calculated. Okay, that I have known. Okay, just multiplying all the elements by minus and keeping this particular element 1 as it is. So you will get minus 1, minus 1, minus 1, and you will get 1 along with it. Okay, from this particular formula. Okay, so this is the answer. Answer would be A. A lot of concepts are involved here. Okay, if you are having any doubts, feel free to go through the online lectures which we have already supplied as well as this PDF. Okay, moving forward towards second question, please take a pen and paper, try to note down. Okay, because these are small concepts. Till week 5 things are very mathematical, but after week 5 till 12 week 12 things will be more practical and uh, uh, you will be more engaged in the content. Okay, so this is my particular observation, but these are very very important. Importance already I have told you that whatever the applications are happening in day to day world are because of these particular concepts only, and they were invented very early. Okay, when the first camera was made, after that only the geometry, the various parameters from late 1990 onwards. Okay, the domain of computer vision has been evolving. And it has been continuously evolving for the past 30 years. Okay, it has been continuously evolving. So these very basic concepts are the base over which the entire domain of computer vision is involved. And till the day I can just say you in this particular fashion that we are able to create an augmented world around us using these particular concepts. Small concept was there in the previous just one question, that how to project a 3D map or 3D coordinate into a 2D plane. So very small concept was there, but the application is very large, because reverse of that, if you are able to perform, then you would be able to create an augmented map of the world. Okay, this is the thing. So very good question it is there. A pinhole camera has a focal length f equal to 1 units, and its principal point is at cx cy equal to 2 comma 2 in image coordinates. Okay, if a 3D point in camera coordinates is located at x comma y comma z equal, equal to 1 comma 2 comma 2, what are the image coordinates after projection? Okay, same thing is there, just we have incorporated one more parameter, that is the focal length. Okay, so we will see the correct option would be option number A. How? In computer vision and in your photogrammetry. Photogrammetry, if I tell you in brief, it is a particular concept, this particular thing. Terms are very, very intriguing or very interesting to note. Another term is there, photogrammetry. Photogrammetry is nothing but creating a stitched map, a stitched map from 2D images. If I tell you that the video which you are seeing is nothing but the collection of images, maybe in my computer it is showing 60 fps, means 60 particular images are being stitched in 1 second to create an illusion of a video. Okay, so similar thing is there in your in your mobile phone or in your device. It might be some another number. Maybe it is 29 FPS. So larger are the number of frames per second. Okay, the smoother the quality is, and our eyes, they are having particular feature that whatever the thing which is greater than 16 frames per second, the eyes classify, the mind classifies it as moving. Okay, this particular limitation is there of our eyes. Okay, maybe if some alien species comes to earth and it is having much larger video frame processing capacity, then it would be seeing us in still frames. Okay, but our eyes, whatever our eyes and our brain in combination, or our visual system, it classifies an object as moving or still if it sees frames greater than 16, okay, in 1 second, then it classifies it as moving. Otherwise it classifies it as still. Okay, so this is the beauty. So photogrammetry is similar kind of concept in which various 2D images are taken. Okay, 2D images are taken at one conjunction with one another. Means they will be taken in still frame. Okay, means a UAV, a drone, uh, is the best example by which I can just talk about this particular concept. Okay, using a drone we can capture the continuous frame of say 100 by 100 plot. But if we want to create a digital elevation model, okay, or we want to know that how our plot will is looking in 3D, as a 3D image, then we will be using this particular concept of photogrammetry. Okay, this particular concept is very, very important. What we do, we just capture the entire video, okay, or the entire still frames we try to capture at a certain frame of rate. The frame of rate would be somewhat lower. Okay, video is generally captured in 30 frames per second, but for photogrammetry we try to keep our frames restricted to 10 frames per second. Okay, now we have captured the entire plot, okay, in 10 frames per second video, as a video. Okay. Now you try to extract all the images, and after all the images are extracted, then you try to create a particular 3D map. That particular 3D map will be projection of all the images on the basis of elevation. Okay, so by the help of this, you would be able to calculate a digital elevation model. And nowadays, whatever the satellites which we are launching and whatever things you are saying, for example, remote sensing is largely based on this particular concept. And photogrammetry is now it is particularly limited to just RGB images. Okay, but those satellites they capture a lot of other band frequencies also, and they try to project them on 3D space also. So whatever the applications which we are just seeing in present scenarios, okay, they are mostly based on the concept of projection, okay, which we are just seeing. This is the thing. In computer vision and photogrammetry, coming main to the main topic, okay, not deviating much from it. A pinhole camera model is a simplified geometric model of how a 3D point in world projects onto a 2D image plane. Okay. Key idea is a 3D point in camera coordinates is projected to a 2D image point based on focal length, based on the principal point, based on the relative depth. Okay, distance from the camera. The pinhole camera model, the core formula, okay, which we just have derived, okay, which we just have seen in when we were projecting 3D coordinate to a 2D plane. Now we would be seeing this as a core formula in terms of our focal length, in terms of our principal point. Okay, focal length is nothing but distance from pinhole to the image plane. Okay, and Cx, Cy are the principal point in image coordinates where the optical axis intersects the image plane. Okay, these are the principal points. Very easily, if you just have seen the optics in class 12th, okay, this particular concept is very detailed taught there. Okay, and u comma v are the pixel image coordinates after projection. Okay, so if you will see the corresponding image coordinates would be u equal to f multiplied by x upon z plus cx, and v would be f multiplied by y upon z plus cy. Okay, just one second. Now you try to see where this particular concept has come from. Okay, projection of a point through a pinhole onto an image plane. Okay, projection of a point or an object onto an image plane, which is this one. Projection of a point through a pinhole onto an image plane by the property of similar triangles. These two particular triangles are there. Okay, if you will try to draw them and if you will try to formulate the property of similar triangles, if you will try to use, then you will get x as f multiplied by these two triangles as well as these triangles. Okay, these two triangles. Okay, if you will just try to see, then you will get x as f into x upon z and y as f into y upon z. And if you will try to project, since the image pixels are defined on 2D coordinate system, optical center may not be necessarily on 0 comma 0, then you need to adjust an offset. Okay, so then you just add this particular offset cx as well as cy to the as a principal point, and you get this particular formulation. Okay, why this particular thing or particular concept matters? Because this model simulates how 3D objects are captured on a 2D plane or a 2D camera. As well as in case of your camera calibration, you need to know f, cx, cz, cx, cy to map has to be mapped to world or image spaces. In case of your 3D reconstruction, if multiple images are available, inverse projection can help your 3D recovery. Okay, as well as in your graphics, as well as in your rendering. This particular concept is very, very useful. What is the summary? The summary says the projection formula is U equal to F multiplied by x upon z plus Cx, and V as F multiplied by y upon z plus Cy. Okay. What is principal point? Principal point is nothing but your optical center or your offset center of the sensor. What is focal length? Which controls the magnification. Shorter is the focal length, okay. Wider is the field of view. What is depth Z? It controls how far the point is, okay. And what is the final image point? It is resulting 2D location on the image plane, and in matrix form, x is nothing but capital K multiplied by normalized x normal matrix. Okay. So if you try to use this particular formula, okay, U equal to F into x upon z plus Cx, and V equal to F into y upon z in plus cy, then you plug the values. Okay, x you try to plug, y you try to plug, z you try to plug, and f you try to plug. Okay, all the values had been given here. You will get f u as 2.5, v as 3, and your option correct would be A. Okay, this is the thing. Now you try to see another example based on these particular pinhole camera geometry. Already in the beginning I told you all the questions are more or less related in the present session to this particular concept only. Okay. Find out the direction of the principal axis of the camera with projection matrix P equal to 96 minus 17 minus 2590 2001. Okay. The principal or the optical axis of a pinhole camera is by definition the line through the camera that is perpendicular to the plane of the image. Okay. And in real world coordinates, it is nothing but P3 transpose into capital X equal to 0. Already taught you that if you will reduce the distance between the image plane and the camera to 0, you won't be able to formulate any image. And that is what has been written mathematically here. Okay. So P3T is the third row of the projection matrix P. Okay. Okay. This particular matrix, third row of the projection matrix P. Okay. That you try to extract. Now you drop the last component or the fourth component, okay, to the normal plane. Okay, then you will get this particular camera optical axis, that is 200, and your correct option would be C. Okay. Yes. Moving forward towards the next question, a camera projection P is given by this particular denomination. All the questions are more or less the same. Okay, P as a matrix, projection P matrix has been given to you, and you are asked different types of questions based on this. A projective camera P is given by this particular denomination. Okay, 8340 1 minus 590 2170 images as 3D line L as L equal to 5 to 7. Okay. Compute the plane found by projected line L and camera. Okay, center. That is the thing. The correct option would be B. How? Let us see. When a 3D projective camera, okay, maps into, means we are creating a relation between three-dimensional coordinates P, okay, P3 and P2. Okay, means we are creating a transform, or we are trying to project a 3D point onto a 2D plane. maps into the m- when a 3D projective camera maps world points to image point. Okay, the pre-image of any line in the image is not a curve, but it is a plane in space. Okay, if you will try to see, a very good example would be from the movie Interstellar. If you have seen it, it came in 2014, in which a scientist was trying to explain the main character of the movie about what is a wormhole. Okay, so he was trying to explain that if you try to see a sphere onto a 2D plane, what would be the projection of a sphere? A sphere is there in 3 dimensions. And if you try to project it on a 2D plane, what would be you would be getting? You would be getting a circle. I still remember from the movie Interstellar. Okay. So same thing is written here. The pre-image of any line in the image is not a curve, okay, but a plane in space. Okay. Plane in space in 3 dimensions would be nothing but a line in 2 dimensions. So union of all rays through the camera center that hits the projection, and here is how it is written here. Image lines and the back projection. In the image, a projective line is represented by a 3 vector L1, L2, L3 transpose, such that any image point X, okay, which is given in 2 dimensions, okay, any image point X1, X2, X3 transpose lies on the line if and only if L transpose X equal to 0, coming from the same fact. If you would reduce the distance between the camera and the image plane, you won't be getting any of the image. Okay, so a 3D point X projects to an image plane X equal to Px. So if X lies on L, then L transpose Px equal to 0. Okay, this is the thing. In your algebra, the plane coefficients via P transpose, that is the matrix, writing P decomposing M and P4 as a 3 by 4 matrix, we have L transpose Px equal to 0. This particularly implies that transpose of transpose is nothing but the same matrix. Please do remember. If you will take 2 times transpose, then it will be same matrix. Okay. We have L transpose Px equal to 0. So P transpose L transpose X is also equal to 0. Then you create the 4 vector as pi as P transpose L. Okay. This will give you further a plane having the homogeneous equation. This particular plane pi transpose X equal to 0. Okay. And you would be also getting this particular denomination, which would be very, very useful. Okay, in our coming questions. Okay. Yeah. So camera center C is the unique world point in which PC equal to 0. All of the rays of light pass through this particular point or the camera center C that is imagined. Okay. Image line L is a set of rays in the image plane. Okay. And back projection, just a second. Yeah. And back projection of L is the union of 3D lines such that EX belongs to the relation L. Okay. And these all the rays form exactly one plane in a space containing C and those projected backwards towards the world point. Okay. This is the thing. Just 1 second. We will proceed towards the question itself. Yeah. It is mattering again for triangulation, for reconstruction, for understanding the scene. Scene understanding means calculating what are the different image of which what are the different object distances from a 3D image or a 2D image. Okay. and in case of your augmented reality, or as well as in case of your virtual reality. This is very important duality. Okay. In which an image line is transformed into a 3D plane. Okay. Underpins much of the projective geometry in vision. Okay. To find the 3D plane that contains both the camera center and the back propagation of the image line L, we use the fact that any 3D point X lying on the plane must project to an image point small x on the line L. Algebraically, L transpose small x equal to 0. Okay. And hence you will get the projective plane pi as pi p transpose L. Okay. P and L, if you try to decompose from the question, then you just have to compute P transpose into coordinates of line L. Okay. And then P transpose P has been as a matrix has been already given to you. Okay. Then L already has been given to you, and P transpose you try to interchange the rows and columns, and then you try to calculate P transpose L, and then you will be getting this particular matrix 56, 12, 87, and and 0. Okay. So conclusion is the plane passing through the camera center and the back propagation of the image line L is 56, 12, 87, 0. That is your correct choice. Okay. Moving forward, the all the questions are more or less the same. Okay. So much of the things to explain was there in the first question only. I already taught you. Okay. There, please do try to solve all these concepts, all these questions, okay, by your own hand, pen, and paper. Then in the examination, you won't be facing any of the problem. Okay. Consider a camera-centric world coordinate system with the image plane parallel to principal plane and its x and y coordinate axes are parallel to those of a world coordinate system respectively. If the principal point is located at 2, 5 in the coordinate system of the image plane, what would be the projection matrix of a pinhole camera with focal length f equal to 3? And options has been given to you. Okay. So you try to see in this particular setup, camera worlds, camera's world and camera coordinate frames coincide. Image plane is parallel. Okay. To the camera's principal plane. There is no rotation, there is no translation since they are parallel. So you can always decompose it as k, I, and 0. Okay. K is the intrinsic matrix. It encodes the focal length f. Principal point is cx, cy. Okay. So k will be f 0 cx, 0 f cy, and 0 0 1. So if you try to plug in all the values, f already has been given to you. Just 1 second. Yeah. F already has been given to you as 3. Principal point has been given to you. Cx, Cy has been given to you as 2, 5. Okay. You try to plug in K and K as a matrix as 302, 035, 001. And I in conjunction with or I relation 0, you try to write it down in this form and manner. Then you will see that, just 1 second, bear with me. Yeah. The full projection matrix will be P equal to Ki 0 means K already has been given to you. I in relation 0 you already have computed. You just have to multiply rows by column. Okay. So since this particular is a 3 by 3 matrix, okay, and this is a 3 cross 3 rows, 4 column matrix, resulting matrix would be 3 cross 4. 3 rows, 4 columns. Okay. So similarly, you try to multiply, okay, and try to see whether you are getting the same thing or not. Okay. Mhm. So you try to match and you would be getting an option number A. Okay. The extrinsics I0 are here because camera frame is same taken same as the world frame. Okay. And intrinsic K has been projected is the main principal point Cx Cy and it has been scaled by focal length f. Okay. Now you try to map the image and you try to build the relation. Okay. Next question. Consider the camera projection matrix P. Matrix P has been provided to you. Two image points x1 and x2 have been provided to you, and the center of the camera is has been provided to you as O. Then you have to find out what is the unit normal to the plane. Okay, you have to find out what is the unit normal to the plane. Okay, this is the thing. Just 1 second. What is the unit normal to the plane O x1 x2? Okay, you try to see here that when you calibrate a pinhole camera has to be calibrated. Okay, it has to be calibrated for what? For the distance. Okay, adjusting the focal length, adjusting the distance between the image and the plane. Okay, all these adjustments are made in order to obtain the image with the maximum resolution, maximum refinement. Okay, maximum refinement image is obtained through camera calibration. Okay, so when you calibrate a pinhole camera whose projection matrix is M relation 0, then camera center O sits at the origin and whose frame is already taken as 0, comma 0, comma 0. Okay, if it is not taken, then you have to incorporate Cx, Cy, Cz. Already we have done in question number 2. Any 2D image point x, okay, written in form of coordinates u comma v, back projects to a 3D, okay, 3D ray whose through O, whose direction up to the scale is founded by this particular denomination, writing the image point in homogeneous form, okay, uv1, and then you try to solve md equal to x raised to power h or this particular coordinate denomination. Now you try to calculate the distance d as m inverse x raised to power h. Okay. Why we are calculating the back propagation? Okay, back propagation of the rays because the 3 by 3 matrix M it encapsulates focal length, it encapsulates skew, the principal point and the rotation, which always matter in case the image has to be calibrated, the camera has to be calibrated, and these are the parameters which affect the resolution of the image onto the plane. Okay, where there is no translation, the projective map is this particular thing x raised to power h or x uh, s m x y z transpose. So to grow from image back to the world direction, we invert this particular matrix M. And the result is the D, which is a direction vector, which in 3D would be capital X equal to lambda B. Okay, it will project back to U comma V. Okay, now you try to see here the plane through two rays and the center. Okay, two distinct image points have been given to you x1 comma x2. Their rays have been given to you d1 as m inverse x1, okay, and d2 as m inverse x2. Then you try to span a 2D subspace in relation R3 and you try to imagine like two sticks both are anchored at coordinate O and they are in the directions d1 and d2 and they will form an image onto the plane OX1, X2. Then you try to compute the normal. A plane in relation R3 can be specified by a unit normal vector n. For the plane sp spanned by d1 and d2, the normal is the cross product d1 cross d2. And the unit normal is nothing but the vector divided by its magnitude. Okay. So if the camera projection is there, m in relation with 0, it has 0 translation. Its camera center is at the world origin 0, 0, 0. Okay. Any image point x equal to u comma v projects back to array through O in world coordinates with the direction m inverse u v 1. So you try to compute the two ray directions. Okay, x1 already given to you 2 comma 5, x2 already given to you 7 comma 9. Then you try to resolve this in homogeneous form and you try to solve for the direction vector di's. Okay, so m into d1 we take it as 251, m into d2 we take it as 791. Then when you will try to compute d1 and d2 and you try to compute the inverse, you will get d1 as minus 2.631 minus 10.054 6.737. Okay, as d2 you would be able to calculate. Don't worry, I'll show you the complete steps. Okay, just bear with me. Okay, then you try to form the plane n as d1 cross d2 and you try to match the options, you will get the option number C. And what in intermediate steps I have just skipped, I'll explain you in great detail. Just bear with me, okay? Few minutes. Yeah. If you try to find out the unit normal to the plane defined by the camera center O and two image points, okay, x1 and x2, and you have been given the camera projection matrix P, the step by step procedure is there. First, you have to find the camera center, then you have to back propagate or back projects x1 and x2, then you have to determine what is the plane defined by the camera center and two rays, then you have to compute the unit normal and then you have to compare with the options. These are the 6 steps which you will follow in this question. First of all, you have to find out what is the camera center. Okay, so camera center O is the point in 3D space such that P multiplied by the center 0 O is 0. That is, it lies in the same plane, null space P. Okay. Projection matrix P already given to you. Okay. Notice last column of your P, projection matrix P is 0. It is suggesting that camera center, it may lie at infinity. Okay, which is unusual, not a possible case. Okay, which is unusual but possible for certain projection matrices like your orthographic projection in 90 degrees or a degenerate case. Okay, let us first of all solve for the null space P. Okay, you take the camera center O as x comma y comma z comma w. Then you try to calculate P into 0 and this will give you a system. Then you try to calculate, since the last column of P is 0, W is not there in the equation. Then the null space may include point at infinity. You solve for x comma y comma z using the Gauss elimination technique or any technique whichever you like. A lot of things are there. Okay. Even you can use the cross multiplication method. You can use the Gauss elimination method, whichever you like. You just have to solve this particular system of equation. Okay. You calculate the coefficient matrix. Now you step by step try to solve, and after solving, okay, you will get these many number of steps. Okay, row 1, row 2, interchange, multiply. You just have to solve the system. Okay, these many steps. Then after that you will get the finally the origin O as 0, 0, 0. You will first get x as 0, you will get y as 0, you will get z at 0. But in just to prove, okay, that I am not writing singularly it as 0, 0, 0, I have encapsulated all these steps in detail. Okay, after the class is over, try to see, okay, and revisit. This is problematic, okay, because null space is trivial, unsolvable. Okay, so but the zero vector here, it is not a valid problem. Okay, 0 last column suggests the camera center may be at infinity. Now you try to again set W as 1, okay, and try to resolve And in the similar fashion, we have calculated the camera center C in question number 3. Okay. You try to calculate C as negative of M inverse P4, comma 1. Okay. M already given to you, P4 you take and you try to solve. Okay. Keeping W as 1. Then it still will satisfy PC as 0. Still we are getting the same origin O as 0 comma 0 comma 0. Okay, hence it satisfies that we the origin would be finally at 0 comma 0 comma 0. You need not to follow all these steps in the examination. In the examination, just whatever I earlier showed you, you just try to solve it. Okay, and mark the option. This I am just doing it for your own curiosity. Okay. What if the origin is not at 0 comma 0 comma 0? That is why I have taken the weight, the option, uh, coefficient matrix W as 1. I will take it as 0 also. So minus 1, 0, 1, minus 2, minus 2 and plus 2. Similarly, you will try to take and just try to satisfy the equations. Okay. This is the trivial proof which I am just talking about. Okay. Now you try to back propagate image point to the rays. Okay. X1 already given to you 2 comma 5. X2 already given to you 7 comma 9. Okay. So X1 is 2 comma 5 comma 1. Okay. X2 is 7 comma 9 comma 1. Okay. Find the 3D rays from the camera center through these image points. You need to directions of the unit. We need the directions of the ray. Okay. So the image point X is u comma v comma 1 already taken. Okay. The projection subspace will be S multiplied by u comma v comma 1 equal to P multiplied by X comma y comma z comma 1 equal to M multiplied by X comma y comma z. Okay. So since P4 is 0, so you try to calculate for X1, you try to calculate and V1, and similar fashion which we have calculated for inverse, you try to follow these detailed steps. You will get all the cofactors. Okay. You need to calculate the adjoint of matrix M. Already taught you in previous sessions how to calculate the inverse. Okay. Now, after getting the inverse, you will get the rays V1 and V2. Then you compute the cross product, and after computing the cross product, you will get the normal vector. Okay. And after getting the normal matrix, you try to normalize it by dividing it by its determinant. Okay. These steps, if you will follow generously, okay, then only you would be able to do this in the examination. But I know most of you would be not very convenient. That is why at the end I'll tell you a shortcut also. Bear with me. First of all, I need to tell you the entire calculation. Okay. Then you compare through the options, you will almost get it as option number C. Similar to that which I have calculated. All these steps are involved till the calculation of the unit normal vector n. Okay. But since the examination is time bound, you won't be having that much sufficient time. I also know this. Okay. So bear with me. I will also tell you a shortcut. Okay. It is there with me. Okay. Alternate method, you need not to solve this entire 3 by 3 linear system, making V as 1, V as 0, W at 1, calculating the normal vector, then calculating the modulus, then calculating everything inverse. Every step is involved. Okay. 6 different steps. If you want to skip, then you need to have a shortcut. What is the shortcuts? You need not to solve this entire 3 cross 3 linear system. Okay. And the 2 cross product, keeping in fact the plane through camera center O and the back propagation of the image line x1 x2 is given by pi equal to P transpose multiplied by L. L is the image line which is passing through x1 and x2. Since P is M comma M in conjunction with 0, first three entities of pi are simply n equal to M transpose L. So if you try to make this plug and play recipe, okay, x1 already given to you 251, okay, x2 already given to you 791. You try to calculate image line L as x1 multiplied by x2 cross product of that. You would get -4, -5, -17. Okay. Then you try to propagate, okay, M transpose L. Okay, M already given to you as 749236158. It came from this projection matrix P only. Okay, written here 749236158. Okay. Then you try to compute N as multiplication of M and your L. Okay, M transpose multiplied by N. M transpose multiplied by N, if you will try to calculate, then you will get as minus 34 minus 86 minus 142. Try to normalize. Okay, 1 upon under root of all the squares of components. Okay, so you will get as 0.20, 0.5, 0.84. So entire job is reduced to 3 steps. I showed you the entire detailed method also, which encompasses six particular steps. Okay, as well as I showed you the steps which you can follow in the examination. Okay, so that you are able to pass this course with flying colors. Okay, the very shortcut method that you would be able to solve within using this particular property, pi equal to E transpose multiplied by line n. Okay, just this is the thing. So if plug and play recipe you want to perform, you can do that. If you want to make through the 6 steps which are involved, you can do that. But my sincere advice to you is that in the examination, follow the shortcut. Okay, shortest path. If it is an objective question, if it is a subjective question, then you will be given much amount of time also. This entire calculation, if it is done religiously, at least requires half hour. Okay, half an hour, because it also took me for calculating, then calculating after that I need to verify also. After step 1 is completed, I will verify once that whether I have computed all the steps, because from step number 1 to step number 6 all these steps are interrelated. Okay, so if you will make a mistake in step number 1, then you won't be able to proceed towards step number 2, 3, 4, 5, 6. Okay, without any mistake. So sincere advice to you is just follow this particular approach also in the examination. Okay. Next, you just take the note of question number 2 and try to solve. I'll be just coming in 2 minutes. Try to read this particular question, note down in your note down in your notebook and pen. Okay, notebook with help of pen. Okay, and then try to solve this particular question. This is very similar to question number 2. Okay, focal length f has been given to you. You just need to map the perspective projective mapping from coordinates 1 comma 4 comma 5, okay, to using the camera image focal length f. Formula already I told you, u comma v, already formula has been taught to you. Image coordinate has been given to you. You just try to calculate. Okay, I'll be just joining in 2 minutes. Okay. Yes. Now, this question is nothing but the adjunction or the continuation of question number 2. Okay. So, in question number 2, already we have been, I have already shared with you that if you are projecting a 3D image, okay, or a 3D plane, a 3D point, okay, or a 3D point on a plane onto a 2D plane, okay. So if you are doing that for a pinhole camera, center, if it is origin and the image plane at a distance f along the z-axis, that is plane z equal to f, any world point which would be there in terms of capital X, capital Y, capital Z, it would be projected. Just one second. It would be projected. Just one second. Yeah, it would be projected onto the image coordinates u comma v via the similar triangles. Then you try to see small u would be nothing but f into x by z. Okay, and small v would be nothing but f into capital Y by z. In addition to that, you can write down plus cx, just one second, plus cx plus cy also. Okay, if the center is not at origin, then you have to remove. If the center is at origin, then you can remove cx and cy also. Okay. So x has been given to you 1 comma 4 comma 5, f has been given to you 0.25. Then you try to calculate u equal to f into x by z. Since the center is at origin, we will use this particular form. We will remove the principal points cx and cy. Okay. So you try to calculate, it would be 0.25 multiplied by 1 by 5. Okay. And v would be nothing but 0.25 multiplied by 4 by 5. Okay. So now you try to see 0.25 multiplied by 0.2 equal to 0.05, that is 1 by 20, and 0.25 multiplied by 4 by 5 equal to 0.20, that is 1 by 5. 1 by 5 and 1 by 20, directly you would be getting option number B. Okay, this is the thing. Just one second. Okay, we'll continue. Yeah. The camera model, already camera center has been taken as 0 comma 0 comma 0. Okay. The image plane is the plane z equal to f parallel to the xy plane. Okay. And 3D point x comma y comma z lies along the ray through the origin. Intersection through image plane z equal to f is found out by scaling the ray so that z coordinate becomes f. Okay. So derivation by those two similar triangles, we will give you f into x by z, f into y by z, and f. Okay. In u comma v, you can always calculate. Why is it projective? Because it's a linear map in homogeneous coordinates. Okay. And points at infinity projects to 0 comma 0. Simple model underlies everything from basic camera calibration to 3D reconstruction. Okay. Yes, given the projective matrix P, in all the questions, projective matrix P is given to you except one question. Okay. Compute the vanishing point of a line in image coordinates with direction ratio 4, comma 3, comma 2. Okay. So now you will try to see. You set up the direction in homogeneous form. A 3D direction ratio of 4, comma 3, comma 2 is corresponding to this particular homogeneous vector. Okay. Project with P. Okay. P as a matrix already given to you. You compute P into D infinity. Okay. You try to compute P multiplied by D infinity and you try to multiply all the values, you will get 10, 15, 10. Okay. Try to dehomogenize. Okay. By getting the ratios U comma V. Okay. U comma V is nothing but X by W, Y by W. You will get. Okay. last component is w. Okay, that would be 10. So you multiply all the sorry, divide all the values by 10. Okay, so 10 upon 10 is 1. V is 15 by 10. Okay, 1.5. That you will get as 1 comma 1.5. Okay, this particular thing, the denomination from relation r cube to r3. Okay, already taught to you how you can represent the x comma y comma z coordinates in n u comma v comma w format manner. Okay, yes, when a family of parallel 3D lines is imaged by a pinhole camera, they tend to appear to converge at a single point, which is known as the vanishing point. Okay, it this particular phenomena, why does it arises? Because points at infinity along the direction get brought back to finite image coordinates by the projection. Okay, representing a direction as a point at infinity in homogeneous 3D coordinates, any finite point is x comma y comma z comma 1, while a direction, a point at infinity, is written as d infinite dx comma dy comma dz comma 0. 0 in the last, it is ensuring that adding any finite translation doesn't move you to any of the direction. Okay, precisely keeping in parallel lines. When you try to project via P, the calibrated camera is described by 3 cross 4 projection matrix. If you multiply P by this homogeneous 3D point, you would get P into XH. Okay, XH is a point at infinity. The product P into XH can have non-zero last coordinate W dash. Okay, that's exactly what creates the finite vanishing image point. Okay, then you try to dehomogenize in which for in the similar manner in which I have dehomogenized the coordinates. Okay, when you have computed, when you have just computed the XH. Okay, then you try to retrieve the usual 2D image coordinates by dividing it by ratio W dash. Okay, then you try to see the direction at infinity is 4 comma 3 comma 2 comma 0. Okay, projection matrix P already given to you. You try to multiply. Okay, then you do homogenize. These all the steps we just have completed. Okay, all these steps we just have completed. Similar repetition is there. Okay, nothing new is there. Yeah, just 1 second. Okay, yeah, yeah. Parallel lines in space have the same direction vector, which is d infinite. Camera projects every point on each line along rays through the pinhole. Okay, as you move further along the line, which is lambda approaching to infinity, the intersection on the image plane approaches a fixed limit u comma v, and algebraically that limit is lambda into d infinite. Okay, you get a finite point as u comma v. This is the concept of the vanishing line. Okay, why these particular vanishing points they matter? They encode the orientation of sets of parallel lines in a single image. Okay, in camera calibration, detecting vanishing points can help recover the camera's focal length and principal point. In your 3D reconstruction and augmented reality, vanishing points inform us about scene's geometry and help place the virtual objects. Okay, just 1 second. I think my screen just got disconnected. I'll just join. Okay, just 1 second. Very sorry for the disruption. Just 1 second, 1 second, guys. Just 1 second. Just one second, guys. Mm. Yeah, now the screen is back. We'll just continue. Okay. I was trying to tell you the concept of the vanishing point of a line. Okay, vanishing point of a line. The parallel lines in a space have the same direction vector d infinite. The camera projects every point on each line along it through along rays through the pinhole. As you move further out the line, the intersection on the image plane approaches the fixed limit. Okay, algebraically that limit is p because lambda cancels out in the dehomogenization. You get a finite point which is u comma v. Why it matters? Because it encodes the orientation of the parallel lines. For example, the edges of a building into a single image. Okay. What is the orientation of a particular line or a particular subspace points with respect to one another? That is the thing. In your camera calibration, detecting vanishing points, it can help to recover the camera's focal length and principal point. In 3D reconstruction and your augmented reality, vanishing points inform us about scene's geometry and they help to place virtual points with the camera perspective, with the correct perspective. Okay. Coming towards the next question, which is a projective camera P has been given to you 3, 5, 4, 0, 1, 3, 2, 0, 2, 1, 1, 0. It images a 3D line which is has been given to you L as 1, 2, 3. Now you try to compute the plane found by projected line L and the camera center. Okay. Mhm. Now you try to see to find out just one second. Yeah. To find out the 3D plane phi, okay, that contains both the camera center and the back projection of the image line L, you need to use the fact P transpose L. Phi is that particular plane which is containing the camera center and the back projection line L. This concept we particularly have used in question number 6 to eliminate 6 steps. Okay, in question number 6, we used it to eliminate 6 number of steps to calculate the exact same plane pi. Okay, already we have used this particular concept and a lot of steps I just saved in front of you. Okay, so you write down this projective matrix P. Okay, and image line L, P you write it down. Okay, image line L you write it down. Then you try to compute P transpose L. Okay, P transpose, matrix transpose, we can do it. Okay. This is a 3 cross 4 matrix. Okay. Line L is 1, 2, 3. Okay. P transpose, if you will try to calculate, then you just have to interchange the rows and columns. Okay. This particular thing, you try to calculate the transpose of the matrix. Okay. Just one second. Yeah. You try to calculate the P transpose. Okay. Now you try to multiply it with line L. L it has been given to you and you will directly get the answer as 11, 14, 11, 0. Okay. Now you if you try to interpolate as the plane, okay, in terms of 11, 14, 11, comma 0, it defines a plane pi, okay, 11x plus 14y plus 11z plus 0 into w since the weight is 0, okay, equal to 0. Because the fourth component is 0, this plane passes through the camera center, that is 0, 0, 0, 1. Okay. Correct answer already you know. It is 11, 14, 11, 0. Okay. Homogeneous 4 vector obtained. Okay. Image line L in homogeneous image coordinates is a line in 3D vector. Okay. L as L1, L2, L3 such that L transpose X equal to 0 for any image point X on the line. Okay, and the back projection. Okay, all 3D points X with Px lying on L satisfy L transpose Px equal to 0. And the plane equation. Okay, uh, P transpose Lx L transpose X equal to 0. So pi will be P transpose L. This exact denomination I have used. Okay, P transpose L. It will give me the plane's coordinates, which is pi 1, pi 2, pi 3, pi 4. Okay. Since P has no translation column here, camera center is 0001. Okay, and pi 4 is 0. Okay, this duality image line for transforming 3D plane containing the center is a cornerstone of the projective geometry in computer vision. Okay, this is the thing. Last question for the present session. Find out the principal point in 2D real space and principal axis vector of the camera matrix P. Okay, and P is a projection matrix already given to you. Okay, correct option would be A. Let us see it in great detail. In your projective camera modeling, okay, projection matrix M subspace 0 encapsulates both the camera's intrinsic parameters and its orientation in a 3D world. Because last column is 0, okay, the camera center sits at the origin of the world coordinates. All rays shine out from 0 comma 0 comma 0. What is the principal axis? The principal or the optical axis is the 3D line through the camera center that ends up hitting the image exactly at the principal point, that is line of the sight. Okay, if we write P equal to M comma 0, M subspace 0, then the columns of M maps into worlds x comma y comma z axis into camera coordinates. In particular, the third row of M, which is M3T, okay, points in the direction of the camera's optical axis, where a points one unit is the M3T, okay, M31, M32, M33, okay, and D is nothing but the non-zero multiple of the vector, which is M31, M32, M33. This is a valid direction for principal axis projection in world coordinates. Okay. So the principal point Cx comma Cy is the point on the image plane where the principal axis intersects it. Okay. In pixel coordinates, this is typically near the center of your sensor. Okay. For algebraic identification, you need to find out the direction D that hits the image plane Z equal to 1. Okay. So if you try to project M into D, you will get U dash, V dash, W dash, and Cx and Cy. Okay, the projective, the principal points you will get as U dash upon W dash and V dash upon W dash. So why this will work? Because M encodes how 3D directions map into image plane coordinates. Okay, third row of M picks out the mapping of the world's z direction that becomes the vertical axis, and projecting the axis vector into normalizing tells you where the uh, image plane that forward direction lands, that is to your principal point. Okay, so putting all the things together, first you have to extract M3T, then you have to compute M into D, then you have to dehomogenize to obtain the principal point Cx Cy. Okay, P is relation M in relation 0, M subspace 0 already given to you. M you try to extract, okay. P given to you, yeah, P has been given to you. M would be nothing but minus 3 minus 6 minus 8, 257, 120. Okay, this you try to see. Then principal axis direction D. By definition, the principal axis is the ray through the camera center that lands at the principal point. Algebraically, third row of the matrix M, you write it down as 1 2 0. Okay, D you write it down as 1 comma k multiplied by 1 comma 2 comma 0, and Cx Cy you write it down. Okay, the principal point is the intersection of the axis with the image plane Z equal to 1. If you try to find out, okay, take the direction vector M3, okay, and you try to project M into M3, okay, then you will get it as minus 15, 12, 5. Okay. So you try to dehomogenize, you try to find out Cx. Cx is minus 15 by 5, that is minus 3. Cy is 12 by 5, that is 2.4. And you get the principal points as minus 3 comma 2.4, which will match with option number A. Okay. Axis direction is third row. Okay. And principal point is M into M3. Okay. Correct solution is A. Principal point of the camera is given by M into MQ, M3. Okay, where M and M3T are left hand 3 by 3 and third row of matrix M. Principal axis vector is km3, where k is an integer. Okay. Now, this marks the end of the 10 questions which I wanted to discuss in front of you all in this present session. Okay. Next, I'll be teaching you some of the applications. Okay. Which you must know, because apart from the mathematical aspects which are mainly taught to you in the your in your what to say, yeah, in your video lectures, okay, as well as in your video lectures, as well as in your the sessions which we are taking, okay. The theoretical aspects are mainly dealt, okay, but you can always look for the practical aspects also. The pinhole camera geometry is used in many real world systems, okay. In case of your 3D reconstruction and photogrammetry, okay, structure from motion, okay, reconstructing 3D scenes from multiple images, used in surveying, used in archaeology, used in cultural heritage preservation. Means if you want to construct a 3D image, 3D heritage, 3D view, okay, then you can use this particular concepts regarding the pinhole camera geometry. Anything which is there, whether it is an image, whether it is a video, is constructed from pixels. Pixels are nothing but the distinct points, x comma y. Okay. Then in case of your robotic navigation as well as slam, slam is nothing but an algorithm, visual slam, Hector slam. These are different algorithms which are used to make draw the line on which the vehicle automatically routes itself. Okay. So AGVs, drones, and autonomous cars use pinhole geometry in visual SLAM to localize and map the environments. So feature points like corners are projected and matched across frames. Okay. In case of your studio vision for depth, two pinhole models are used to compute disparity in depth, and essentially in studio cameras for object detection, this particular concept is very, very important. For your AR, for your augmented reality, virtual objects, they have to align with the real world coordinates. Pinhole geometry will be exactly used. Okay. In case of your camera calibration, eliminating the intrinsic parameters fx, fy, cx, cy, and the extrinsic parameters in case of your rotation, translation, all the factors have to be aligned in order to calculate the distance d. That is the exact distance. What is the distance between the camera and the person, and how to interpret that image, that you would be always only able to deal, okay, only able to deal when you would be facing this particular concept, okay. Rotation, translation, all these concepts, if you would be having a command on, then you would be able to interpret the image, okay, which is coming from the camera, okay. Used in industrial metrology, quality control, robotics, okay. In case of your precision agriculture, mapping crops and fields from UAV and AGV cameras, okay, used for plant health monitoring, road detection, fruit controlling. These particular applications are limited to precision agriculture, but in every domain whichever you will see, the we are trying to leverage the concept of computer vision. In case of your sorting, in case of your grading of various types of mechanical parts, also this particular concept is very well used, okay. For your motion capture and tracking, for your sports analytics, for your biomechanics, for your animation studios, you can use the pinhole geometry to map motion into the virtual models. Okay, that is the thing. These few are the examples. Okay, particularly theoretical examples. Already I have talked you about these. Just give me 1 second. I'll also show you some of the practical example from my own research. Okay, just give me 1 second. I'll open the presentation and I'll show you what are some of the practical examples, because some of the students always ask, sir, after relating to all of these concepts, okay, what exactly we are getting. Okay, what exact thing which we are getting and what exactly are we looking for. Okay, so this we will just try to see. Okay. Okay. Yeah. Now you try to see this particular slide. Okay. In this particular slide, I have used the concept of path planning. Okay. This is my own research paper in which I have planned the path of a robotic vehicle. This one is the robotic vehicle. In the center itself, you can see this particular robotic vehicle along with the the lidar sensor is placed on top of it. The lidar sensor is giving us the 3D it is giving the 2D reconstruction. Okay, using the Hector Slam algorithm, which I just taught you, it is giving us the 2D representation or the 2D mapping of the entire area. And after that, through mapping and localization, I am able to formulate the path planning. Means if I have been given a starting node and I have been given a goal node or a point from point A to point B in which I have to traverse, then since I know the terrain, okay, and I know it in two dimensions, okay, I know that what is the different coordinates, what are the different meaning is this, what are the different distances of the obstacles because of I know the data, because I know the terrain, because I know the 2D mapping of that particular terrain, I would be able to calculate what is the exact path planning from source goal to the node goal. No, to the goal node. Okay, I spoke reverse of that. Node goal. It is goal node. Okay, that is the thing. And in the other slide, I already have showed what is the different steps which I took. Okay. First of all, I mapped the entire AGV. Okay. I mapped the surrounding. I applied the Hector Slam algorithm. Then I mapped the entire LiDAR. Then I factorized and I calculated X, Y, Z, R. And then I actually taught the robot that how you can traverse from point A to point B autonomously based on the calculation of the obstacle. So it will traverse and the entire distance in multiple distances. Okay. For this particular algorithm, the stretch of the robot which I have taken is nothing but it is nothing but restricted to half of centimeter. So it will traverse half centimeter, then it will check what are the obstacles, what is the new parameters which are there around it. So in those many small number of steps, it is traversing through point number A to point number B. Okay, that is the thing. Mm. This is the basic of your robotic navigation. Okay. Now, if you understood it, then I will talk in brief. Just one second. Okay, I will talk in brief about just one second. Then I will talk in brief about your computer vision application. Okay, just one second. Just one second, guys. Bear with me. Okay. Yeah, just one second. If you try to, okay, I haven't projected it yet. Yes, now I'll be sharing my screen. Yeah. it is shared with you. Okay. Now, if you try to see in this particular slide, I'll zoom in for you. Okay. If you try to see in this particular slide, okay, the crop row identification which I am doing, I want to navigate the vehicle which I showed you in the earlier slide within within these two particular rows, okay, of the crops. Okay. So first of all, how I am doing this particular job, I am identifying the crop rows. Okay. First of all, the principal application is this, that I have to extract in this particular video. You can see that through color mass segmentation, through threshold imaging, and through green color mass segmentation, canny edge detection, as well as through grayscale image. First of all, I am segmenting. I am segregating the entire crop row which I would be getting through my robot. For that, I have used a RGB camera, and then first of all I have to detect the crop row. After I have detected the crop row, then I will here I have used another algorithm which is YOLO V8 for segmenting the. First of all, I have detected, then I have segmented also the crop row. After these two particular steps I have done, then what I am doing, I am calculating the inter-row distance. This is the principal application of the computer vision only. Okay, here you can see that through a RGB camera and through a microcontroller, I am able to do this particular task. Okay, so average measured distance I have shown here, what is the error percentage and what is the actual distance. These all things, all the parameters I have shown here. So here you can see that through the computer vision, application of computer vision, I am calculating what is the inter row distance. After the inter row distance is calculated, then I am able to autonomously crop row. I am autonomously able to traverse within the rows of the crop and able to turn also, and this vehicle will come on its own. So the principal application of computer vision, as well as here you try to see obstacle detection also. Obstacle detection is there, then it is avoided using another sensor, ultrasonic sensor. But the principal application of the computer vision which I wanted to show you in front of you is this particular one only. Okay. Computer vision is very indeed helpful for us within autonomous navigation. Okay, this particular application I have done, okay, and I have done through it in a lot of steps. If you are interested in future also, you can ask me. Okay, but these principal steps, calculating the projecting the any point into 3D point onto a 2D plane, reconstructing the 2D point into a 3D image, these all the concepts are very important if you want to create some practical applications like autonomous navigation. This is what I wanted to show you. This already I have done in my own research. Okay. So if you are interested or in future you want to work on those particular domains, then you are very much welcome. Okay. This is the thing. In the previous class, some of the students were asking, sir, after learning this much whole mathematics, what is the application? So this is the application. Okay. Yes. Any issue? Yeah. Okay. So this is marks the end of our class. Okay. I already taught you all the 10 questions. Okay. Along with the applications I try to show you. Okay. If you have any doubts, feel free to ask. Otherwise, you can kindly leave. Okay. Feel free to join the session same time next week, same link. Okay. Thank you all for joining the session. Okay. Thank you. Yes, I can provide you my mail ID. Just one second, I will provide in the chat box. Okay. Okay. Yes, this is my mail ID. And if you are very much interested in this work, then feel free to contact. Okay. Anytime you can contact. I will tell you in detail how to approach this particular work. Okay. Principal applications of computer vision. A lot of students who have joined this particular course are very much interested in the principal applications of this. Okay. But the applications are only done in either your BTech projects, either through your BTech projects, either through your MTech projects. Okay. So that is where you can use these concepts which we are teaching, okay, and apply those in real field. Yes. Okay. Thank you so much for joining this session. Okay. Thank you so much. Do join the session next week, same time, same link. If you have any doubts, feel free to ask. Okay. Otherwise, you can kindly leave. Okay. Yes.
Sir, is that possible to share those slides that you just discussed
Yes. Yes.
about your work?
Yes. Yes. I'll just give you the link. Just 1 second.
Also, I have some questions like, is
Yes.
that
Yes.
possible to integrate VLMs in this kind of a work? Vision
Williams.
language. Okay.
Williams. Please
No,
repeat.
VLM, vision language models.
Yes, 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 yes. It is definitely. Nowadays, these are the topics which are having a lot of scope. Okay, you can try to integrate that particular language modeling also, as well as my sincere advice is to you is pick a domain. Okay,
Okay.
pick a domain, then try to master it in full. After you master it in full, okay, then only you try to see the other domains. Okay, if you are very much interested, then feel free to pursue it. Okay, first of all, if you want to know what are the steps, okay,
Mm-hmm.
have you got this particular link? I have shared in the chat box.
Uh, Wait a second. Yes, I got it.
Okay, okay, this is the link for the all the handouts, for the videos, recorded sessions and everything. Okay.
Yes, yes. Not only for this session, but you also describe about your work.
Yes,
Uh,
yes, yes.
uh,
For getting, no, no, that
that's
particular
it.
PPT I cannot share. Okay,
Oh,
since
okay.
I am pursuing this particular project. Okay,
Mm-hmm.
the research
Got
papers you can always see. Okay, all the research papers are available. Okay, I'll just give you the link of my Google Scholar profile. You can see there. Research papers are available. Okay, there you can see what type of algorithms I am just making. I'll provide you the link. Just give me 1 second.
Actually, I tried submitting a paper at CVPR this year, but
Okay.
somehow I couldn't complete that.
Okay, okay.
So just let me know if I can contribute to research papers as well.
Okay, okay, okay. Definitely. Definitely. I'll tell you. Just one second. Yeah. Yeah. This is my Google Scholar profile. You can go through it. Okay. Yeah. And regarding the visual language modeling, first of all, the principal steps which are there to just master one domain is first of all go through the basics, primary basics. You try to go through them. After that, pull a principal, find out the principal research gap. Okay. For writing a research paper as well as for mastering a domain, this should be your flow. Read the research papers. Okay, through various sources, you try to read the research papers. Okay, then you try to find out what is the research gap. If you find out what is the research gap where the researchers are lacking, then you try to pursue your own research in that particular domain only. Okay, in that particular domain, you would be facing a lot of practical applications, practical problems. Okay, so a lot of researchers would have been worked, so you try to go through it. Okay, then you try to introduce something new. After you have introduced something new, you have compared the results with your peers and you have found out some superior results. Then you come to the next step, that is material and methods as well as the results and discussion. You try to write them down and try to for nowadays the research community is very much interested in GitHub repositories. So you try to jot down all of your results into a GitHub repository, into a GitHub repo, as well as open source profiling. You try to make it down and show your results into the research paper. And after that, you write down the conclusion part. These are the five steps of the principal research paper: introduction, review of literature. After that, at the end of review of literature, you have to provide the research gap. Okay, then you come to material and methods, then you come to the results and discussion, and at the end you give the conclusions as well, along with the future scope. If you follow this particular approach religiously, then your research paper will get selected anywhere. Okay, this is my sincere advice regarding research as well as career building also. Okay.
Yeah,
Yes.
actually, I work in the field of AI with one of the reputed company.
Okay,
It's
okay,
a French IT company.
okay,
Uh, yeah, so I am already aware of the practical application in this area.
okay, okay,
Uh, the thing is, I just need to project it in some way. So
okay,
that's where I'm lacking, and I have completed my masters, and I already completed some dissertations through that. Some of the things I already know,
okay,
and something, as I said, that could be the added things which
okay.
can lead me to a successful paper submission.
Okay, okay. Then you can share the work. Then I'll also try to contribute along with you. I'll try to experience. I'll try to share my experience. Okay. In
Sure.
the
I
similar
have
way.
those papers with me, but it is just that we have to discuss it. If you share some time so that I can schedule the call and then we can discuss it.
Yes, yes. You can take this Gmail. Email me only. Okay. Anytime you can make a Gmail. Okay. Out of the official hours, preferably. Okay. Mainly, I
Oh,
am free in the forenoon also, in the afternoon also, but whatever time suits you, just
uh,
intimate me. Then at the same day, I'll reply to your mail. Okay. So in
right, yeah.
on any Gmail on any meet call we can discuss. Okay.
I tried joining the CVPR workshop, but for some reason, because due to
Mm-hmm.
some personal reason, I couldn't continue working on that. And the issue
Okay.
was only with the template. They said the topic is very nice, contents are good, but
Okay.
since it is not in that specific CVPR format,
Okay.
they cannot accept it because they get several submissions and they have to
Okay.
select few out of them.
This is with a lot of journals as well. Okay.
Yeah.
So you just try to show me what is the template and what is the format in which you have written your research paper. Then I'll be able to just tell you
Sure.
that where are you lacking. Okay.
Sure, sure.
Okay.
Thank you so much for your
Okay.
guidance.
Okay.
We
Okay.
will connect shortly. Thank you.
Okay. Okay.
Bye.
Bye. Okay. Thank you all for joining the session. Do join the session next week. Okay. Same time, same link. Okay. Thank you all. I'm ending the session.